So when we are using this CNN, we have an image and input, a training set, and we have suppose different classes like bird, sunset, dog, cat. These are the classes. And what we can do is using our input, we train the images. We train this model to say that the image that we entered is a bird or is a sunset or a dog or a cat or and so on. Like we can use different networks here, and we can use some algorithms like back propagation to train them, and we can use a lot of learning modes to this CNN. It is, we will not go in depth about how it works, like the coding part of it, but I will tell you that what it does, and what it does is it can learn to classify image, and we can predict and evaluate. We can evaluate its prediction, the quality of its prediction. For example, we can say that this kind of neural network, suppose if we are trying to train a model with some 1,000 images, we can say that it will evaluate with lesser accuracy than a model that's training with suppose 1,000,000 images. So we can, by using some kind of matrix factors like error rate, we can say that which model is better than the other model. And here we have an image, and we have some layers. We call it pooling layers. In this image, since this image is, it could be a big image. Suppose this image is 100x100 image. If we want to feed this image to our network, we can't just add it, use it as a whole. We have to, because otherwise, if this is 100x100 pixel image, then these neurons would be 10,000, 100x100. So we have to break it down to smaller portions, and suppose this small portion could be of 10x10. We call this a sliding window, and we slide it over the image. And suppose we take this portion, which is 10x10, and we feed it to the pooling layer, and then we slide the window, and then we take next 10x10 to another layer. And what these pooling layers are doing, they are extracting the main features, and they're filtering out the details. For example, it's a 10x10 image. What this pooling layer is doing is extracting the main defining feature of this block. Suppose that feature is of 2x2, and then we are sending it to the next layer. And then this after these layers are called pooling layers, and max pooling is like a technique to do pooling. And use the output of the pooling layer, we send it to our network, and this network we can train and then classify easily. Sometimes to make it more simpler, for example, suppose we have an image of a road, what we can do is use some bounding boxes which are used to detect some objects. And suppose we have a tree here, and then there is a car here, and then there is a curb. We can or some kind of traffic light. We can use some bounding boxes to box these objects, and then we can run our CNN on it. What it can do is it will only be acting on the part of image. It won't be acting on the whole image. But even they are, for the images, it depends on the image, but if the image is high resolution image, then it would be computationally very expensive. So in other algorithms like RCnn and fast RCnn, what we're trying to do is we are trying to reduce the computation. And these are very state of art and currently being used in very high tech companies. But we should also discuss what are cons of this technique. One good thing about it is that it is very highly accurate, but the con is that it is very computationally expensive. And to make it simpler, we use some other applications, we use some other algorithms to make the application more similar. One other con could be that this algorithm, right now we're discussing about applying it on an image. Suppose we don't have an image, we have a video, and we have to perform the CNN on a video. We will have some frames, and in these frames we can apply CNN, but what losses that it suffers is that we can't label all the frames accurately. Sometimes we can't give them a context. What we can do is, for example, if we have a video of someone packing stuff in their home and putting it into a box, we can look at a box filled with some household things, and we can say that this box is a packing box, but that box could also be an unpacking box. Like, it could also happen that in the next frames people are taking the stuff out of that box. So what we see in the image is not the whole picture. We should have some kind of context, which will happen when we have some previous frames and when we have some frames after that frame. So context cannot be applied on a CNN because they only act on the image at hand. They can only act on our current image. So what we can do is we can use some other algorithm that use the temporal features. These features are called spatial features, but we can also use some other algorithms that include the temporal features. And that kind of neural network is called recurrent neural network, or RNN. And these networks, they retain some information about what already has been processed, and then we can use it in the decision making. We can use RNN also. Like this, when we are processing a video, just CNN is not enough. We also use RNN, which is also state of the art CV technique. Next, we have RCnn. This RCnn and the RNN are not the same things. This RCnN is region-based convolution network, not the recurrent convolution network. What this RCnN does is, I told you about the two drawbacks of CNN. One, that it is very computationally expensive, and the second, that it is only acted upon the spatial features and not the temporal features. So we can use this region-based convolutional network method to find the regions which are likely to contain the objects in the images. So what we do is we propose some regions using some selective search algorithm, and like this is our image, and suppose we shortlist some regions in it, and these region of interest, we propose them to be, suppose, 2000, and then we perform the convolution over these region of interest. So what we are doing is we're not using the whole image, we are only using the regions that are we have shortlisted using some algorithm. One of them is selective search algorithm. So then we run CNN on these regions, and the result of the CNN, then we can feed it to our support vector machines, and we can use some regression methods to optimize our bounding box boundaries. So I know this is a lot to take in, but I will just simply explain it to you again. Maybe that these first, what we are doing is we have this tool called CNN, and this what this tool does is it takes in an image and tells us what that image is. We classifies the image. In this method, what we are doing is not taking the whole image and feeding into the convolution network. We are taking just the some region of interest from the images. We're taking some regions of the interest, we're feeding using an algorithm to find these regions of interest, and then we are feeding those regions of interest to our convolution neural network, and the results from the convolution neural networks, we are taking them and feeding it to support vector machines. And now what is support vector machines? Support vector machines are also a classifier. What a classifier is classifies the image. It says that image has the object or not. Like it's a binary. It says that it has that object or it doesn't has that object. And we can use some models in support vector machine, like we train the convolution networks. We can also train these support vector machine models, and based on their output, we can predict that whether the object is there or not, or we can give a class to that object, whether that object belongs to a class animals or whether that object belongs to a class humans, pedestrians, or trees, or anything. And we can also apply bounding box regression to the output of convolution network. Now, what a regression is nothing but suppose an equation that tells us the relationship between two variables. Suppose we have an equation of a line y equals to mx plus c. So we have a independent variable, say x, and a dependent variable, say y. Y is dependent on x. We have a relation between them. What a regression does is it finds that relation, it finds that equation, and when we are using some bounding boxes, we suppose this is our box and we only have object in this area, and this is not useful to us. So what we can do is, using bounding regression, we can eliminate this part, this gray part of the box, and we can only select the white part of the box that is needed for us. So linear regression for bounding box offset, we can offset is like we can calculate if this is the box that has the object and this is this part of the box does not has the object. And we have SVMs to classify regions with, we have SVMs to classify the output of convolution networks. And so the advantage of using this is that it is less computationally expensive than CNN, because it's not applying on the whole image rather than some regions only. But the cons is that it is very slow to train and it requires a lot of disk space, and even the inference, like prediction, is slightly slower than CNN. So to improve this method, we have some other methods too. We have a fast RCnn. What a fast RCnn does is, instead of just finding some region of interest from the image, what we do is we first extract the features, and then on the features we perform some selective search to find the regions, and then we perform convolution on those region of interest. So this is our input image. And this convnet is, we are extracting our features through convnet, and we have, suppose, conv5 feature map. In this feature we are extracting some region of interest and using the region of interest, again, what we're doing is feeding it to FC, which is fully connected layers, which is our convolution neural network. In these convolution neural network, instead of feeding it to support vector machines and the regression that we did in the previous slide, in the RCnn, in this we send it to a softmax classifier. Now there are a lot of these terms might be really new to you and you might not understand, but what they do is they support vector machine. What it does, it only, yeah, just to summarize that, this is faster than the previous algorithm because this algorithm is not applied on the image directly, not even on the region of interest. It is applied to the, first we are extracting the features, then the region, and then the CNN is applied. So it is only applied to an image once. That's why it is much faster in performance. Thing is, it is computationally, it is complex to implement. That is the con of this algorithms. We have some applications by Google that uses these algorithms, like Google Photos. We have it in our phone. We can back up our images in it, and what we can do is sometimes it features the best photos from the group, and those best photos, how is it predicting the best photos? It uses some machine learning algorithms to predict the best photos. And we have Google Cloud Vision API. What it does is it's not a free API. What we can do is download some annotated image, because when we are using computer vision in our applications, we need to train it over a lot of data, like in millions, or a lot of image to make the accuracy go higher. So we don't, if we are a small startup, for example, or a medium scale company, we don't have the resources to do the training, and we can use this Cloud Vision API to train the data and download the images. But it also, this API is itself trained, and if you feed some image with text in it, it will give you some text. If you feed some image in it to ask, identify, or classify that for you. And we have Google Lens. We are studying the case study of Google Lens. What it does is, it's also an app by Google. What it does is, you can translate a text in it. You can suppose if you are looking at a picture and you want to see a picture of some dress, and you want to see what shoes goes on with that dress, you can use this Google Lens app for that. You can see what's popular on the menus. You can explore nearby places, like which places you should go to, which restaurants are nearby to your home. All the things, like if you have a heritage monument, you can use Google Lens to see what monument is that and what history Google has about that monument. It can identify plants and animals. It can help you to do your homework, and it can help you with mathematics. Suppose you have an equation you want to solve, you can write it on a piece of paper and use this Google Lens API, Google Lens app to help you solve the equations. So we are looking at the text scanning. We can have text scanning in two ways. We can have instantaneous text scanning or user tab. So in some phones that have higher good cameras and high processing rate, we can use instantaneous. And the other is user tab. We can capture an image, then process it. After we capture an image, we if you're scanning some text, we have to do some character recognition. We use OCR for it, and the algorithms that we discussed in the last slides, regional proposal networks, which is a part of RNN, FastRNN. Google uses it in its Google Lens app, and after we identify the characters, we do text recognition, which involves, like, these texts are written in the straight line, Sometimes we have some, due to some deformities in the image or alignment issues, we have some text in curved path or something. We can use this. They use this text flow technique to read the text from the curved path. And these models, they are trained from a variety of sources, from the recaptchas that we enter when we are visiting some website to the scanned images of the Google books. So we can also, Google also applies some context to it, not just directly capturing the image and telling you the corrections, but it utilizes a knowledge graph that uses contextual clues, and it can tell that this word is a proper noun or this word is not spelled correctly, and it can make it correct in the, and it's using this app, and it uses convolution neural networks to detect text blocks like columns or that are consistent style or color, that this is together, this is a column, and it should go like they should read this line, and then this line, this goes like this. And within each block it uses text alignment, that there is this alignment here, for example, and Google Lens reads the alignment also. And we can look at the language and geometric relationship between the paragraph to determine the final reading order. We have an image that is not properly captured, so we have a warped perspective of the image. So what this app does is it also corrects the perspective. It can correct the homographic distortions. So current market trends in India is I have discussed this research report by Analytics India magazine, and the Indian computer vision market is currently valued at 2.4 billion as of July 2020. This is the latest report, and in this report it says that although the preferred destination for IT transformation services and digital services and software technology operations are in India, but the computer vision has been set up across the India, not entirely, but this is about to change. According to this report, currently close to 35,000 computer vision personnel are working in Indian enterprises, but around 22,500 positions are related to computer vision jobs that are needed to be filled. They are empty, and they want people like you to apply for that job, to learn computer vision and work in their companies. So this is the market size by the company type. So most of the computer vision jobs are in high-tech companies, in MNCs, in companies that work on semiconductors and electronics. Some of these, then the next is domestic IT companies. Some consumer and retail companies use computer vision, engineering. These are the startups that use AI and computer vision. Then there are some domestic firms, consulting firms, public research institutes, like some research institute, even the universities come under the public research institutes. So mostly MNCs in India hire computer vision engineers, but it's not just limited to the MNCs. It can also happen in the other engineering, or not just engineering, retail or consulting firms, or in education. This is the salary-wise distribution of the people who work currently in computer vision field in India, and mostly people who are getting salaries from 3 to 6 lakhs. They consist mostly 27% of the total, but we have as we see that there are people second highest in this category of 6 to 10 lakh, and we see that the median salary of the computer vision professional is 12 lakhs, which I think comes with the experience of. And we see that Bangalore has the highest median salary at 13.6 lakh, which is followed by Mumbai and Delhi. We cannot see this in this graph, but I inferred it from the research report. And the salaries of people working on computer vision in Delhi is around 12 lakhs. Experience level. So given that this field is pretty new, the median experience of people who are working in computer vision is not so great. It's only 5.3 years, and the lower median experience level highlights the nascent nature, that it is new in India. And this is surprising that Chennai has the highest median experience level. People who are working in Chennai, they have most startups, and they have a lot of people who have higher experience than other parts of India, which is followed by Bengaluru with 5.5 years experience, which is followed by Delhi, Mumbai, and Pune. Most people that have high experience in the field of computer vision work are from. So we have growth rate. Because of current pandemic, the growth rate has reduced, and it is now expected to be 3.5 by the end of this year. This lower growth rate is attributed to recessionary effects of current market, and maybe it will be experienced till 2021. And after that, it is expected that the growth rate, this is compound annual growth rate, will increase in computer vision field to up to 9.2%, which is actually higher than the global growth rate. And by 2025, we expect that CV market in India will be valued at 3.6 billion. So job search, while searching for a job, computer vision jobs in India, we can search with the keywords like computer vision engineer, but it's not the case. Often we can use the keywords like machine vision, robotic vision, image processing, image analysis, or some other keywords that use the skills that we do in image processing or computer vision, not this title of computer vision jobs. This keyword will not fetch you that many results, but other keywords that will define what you do, like you work in robotics, you work in machine learning or data science or image processing, or even app development, they will fetch you some job titles about the company. And you can also look for jobs by using keywords like simultaneous localization and mapping, HOG, or these are actually the technical algorithms that we use in computer vision, and they can fetch you more jobs than just this word computer vision. These job profiles could be related to not only to softwares and IT, but algorithm engineers, computer science analysts, and it's actually not just limited to this. Also, like I studied electronics, and now I am also studying mechatronics, and this is like we see that computer vision is applied in a lot of applications. So not just computer science people, a lot of people from other backgrounds can also look for jobs in computer vision. These are the companies that are currently hiring computer vision engineers in 2020: Qualcomm, MathWorks, NVIDIA, Intel, ETM Systems, Bosch Group, Google, and not only this, many other startups. And these, you will ask me, how did I come up with these companies? I searched on platforms like LinkedIn or Indeed or Glassdoor. I went to their job portals, and I summarized that these companies are hiring more computer vision engineers in 2020. So the domain knowledge that a computer vision engineer needs could be not just limited to software, could be in language processing, machine learning, software development, in robotics, mobile applications. It could be one of them, could be all of them, could be some of them. And this, in most cases, in most jobs, they require advanced education. Some requires master's degrees, some requires PhD degrees, but that's not the norm. That's not fixed for everybody. And we may need knowledge of image processing, GPU computing, deep learning, C++, Linux systems, Python. These are just the things, the tools that we need to develop an application in computer vision. And they are helpful in success of the job. Apart from the skills, I also recommend that having an attitude towards learning and being curious is also very important when you are working in computer vision field, or if you want to work in a computer vision field. So I think that's it for me now.